So this is a statics problem I encountered not too long ago, and I'm reproducing the thing from memory, and so I think I have everything right. Also, whenever students are doing these problems, this problems are presented online, and a lot of times each student has the same problem but with slightly different numbers in it. So for example, I have a 16 degrees here. Someone else may have been presented this problem with a different angle, and also the problem said that it takes 40, I believe it was 40 pounds to break any of these ropes. This is a rope that goes over a pulley. This is a rope right here, and 40 pounds to break the rope. Okay, and usually I like to produce, I like to start with blank paper to do these videos. However, the last video I did ended up being 37 minutes long, so I decided to start with some things pre-done, pre-drawn here. So here's, I think the first step for me would be to say that our coordinate axis is going to be oriented like this, so that my y-axis is parallel to this rope right here. And then we're going to do the good old-fashioned, tried and true free body diagram. I'm going to pull this other page out so it doesn't show through. Alright, so now here are the vectors representing those ropes, right? And real quick, since this is a single rope right here going over a pulley, we know already that the tension in this rope is equal to the tension in that rope. So back to our free body diagram, these are the ropes going over the pulley. The pulley would be right in here. So we know that the magnitude of this vector is equal to the magnitude of that vector. And if we draw a triangle to split these vectors into horizontal and vertical components, I'm just going to draw a dotted line right here. These are the triangles we would draw. I'm not drawing vectors, I'm just drawing the sides of the triangle. Okay, so, and the way the problem reads, this whole thing is at rest, because this class is called statics, right? So there's something or someone pulling right here, the weight is here, and everything is sitting static. And the question says, what is the maximum weight we can have here, and what's the maximum weight? And so obviously our limiting factor is one of these ropes breaking. Alright, so back to the free body diagram. If this vector is all y component, it's vertical, so it's the whole vector, the magnitude of this vector is all in the y direction. But these vectors are the only ones that give us any forces in the x direction. And we see that as far as x direction goes, this vector is to the left. Oops, didn't mean to do that. Down and to the left. This one's down and to the right. So this one goes to the left. This one goes to the right. So these are already in opposite directions. So this is going to be a negative. This is going to be a positive. And we know that they have to cancel out because there's no x direction forces from this vector. The only x direction force is here, and the other one is here. and this whole thing is static. So that we know that whatever component, whatever vector we find here, x component, has to be equal in magnitude to the x component of this vector. This is the x component of this vector. This is the x component of this vector. So we know that this vector has to be equal to this one. We already see that they're in opposite directions, so they're going to tend toward canceling. This is negative, this is positive. Alright, so what I'm working up to is that we see that if the magnitude of this vector is the same as the magnitude of this vector, and we know that because, again, this is a rope going over a pulley, and we know that in order for this thing to remain static, this vector must be equal to this one. So here's what we've said. This must be equal to this, and this must be equal to this. In order for that to happen, this angle right here has to be equal to this angle. Because this vector, let's call it T for the tension in the rope, and we know that this one is also T, same force, same tension. And this angle, to get this vector, it's going to be the side opposite, right? So opposite is sine. So let's call this theta and this one alpha. Alright, so this vector is going to be, I'm trying to think of how to designate that vector, but this vector is going to be equal to T sine theta. And this vector is going to be equal to T sine alpha. Alright? And we already said that this has to be equal to this, which means this has to be equal to this. Well, the only way for that to be true is if theta and alpha are the same angle. So we now know that this angle has to be equal to this angle. We don't know what these two angles are, but we know they have to be equal. So let's go back to the original and see if there's any hint as to what those two angles are. Alright, so if we look carefully, this dotted line is a continuation. It's a line of action, we could call it, for this vector. So this vector and this line of action are along this rope right here. So let's extend this line of action for the rope. Alright, so this dotted line is essentially the same as this dotted line that I drew down the middle here. Alright, and so now we see that theta is here and alpha is over here, but we just proved that they have to be the same, so I'm going to call them theta and theta. Hope that makes sense. Now, this is 16 degrees. It's given in the problem as 16 degrees. So we see that this is a vertical line, and it's going to be parallel to this vertical line. We know this is vertical because it's just a weight hanging on a string, and anytime you hang a weight on a string, it hangs straight down. So it's vertical. This is vertical. This line is parallel to this line. So it's not too hard to see that this angle equals this angle. So theta is 16 degrees. Now, that's what gets us a long way toward figuring out the answer to this problem. They say that the rope is going to break if we have more than 40 pounds of force. And we can see that the force in these two ropes, the vertical components are going to add up. So we know that most likely this rope is the one that's going to break first. So it's going to be 40 pounds. Alright, now the vertical component for this vector is going to be T cosine 16. And the vertical component for this vector is going to be the exact same thing, and they're both pointing down. So there's going to be two of them. So it's going to be 2t cosine 16. And now I can take that, since they're pointing down, I can call that negative. Sorry, I don't really have room for my negative sign there. And then this is 40 pounds pointing up, so we're going to call that plus 40. And since this is a statics problem, we know it's not going anywhere. We know that if we sum all the forces in the y direction, that it's going to equal 0. So now all we have to do is subtract 40 from both sides. We have negative 40 equals 2t, that's negative 2t cosine 16. If you guys are struggling with any of this stuff, the angles or anything like that, I would strongly suggest that you go back and review your trig. A lot of people like to remember it as SOHCAHTOA, and that's sine theta equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse, and tangent theta equals opposite over adjacent. I'd strongly suggest that you memorize this and work with it a little bit, because that's what we're using here, and you're going to use it in statics very often. Alright, so now I'm going to divide both sides by negative 2. So that gives me positive 20 equals t cosine 16 degrees. Now I'm going to divide by cosine 16, so I'm going to have 20 over cosine 16 equals t. And let's grab the old calculator, and we're going to say 20. My calculator is a little different than what you're used to. There's 20, enter, 16, enter, cosine, and divide. So the tension in the rope is going to equal 20.81, and that was pounds. So there it is. Please subscribe. This was a statics problem at Georgia State University Perimeter College, Dunwoody campus. So please subscribe and make comments below. You can ask me about if you have another problem, another similar problem that you're struggling with. Let me know. I can probably help you out. Thanks.